Washington State University. Go Cougs!
Welcome back to the course on statistical inference. We're in Module 2 where we're talking about the different classification methods, and in Part 4 we'll be looking at neural networks. So neural networks come in a variety of forms. The type of neural network we'll be looking at is called a multi-layer perceptron. And the idea is that the individual nodes of the network that are designed to model loosely the human neuron were initially called perceptrons. And when you put these perceptrons in multiple layers and connect them up, then of course we have a multi-layer perceptron. So that's the general form of the network that we'll be looking at. Now here is an example of a small network that we might use to do the prediction task we're trying to do, namely predict activity from sensor values. So let's run through how this would work. So at the input layer of the neural network is where we input the data or the sensor values or feature values. And generally these nodes at this network are designed to just pass along their values and distribute them to the various nodes of the next layer. We also typically in each layer have what's called a threshold unit whose input is always 1. And this allows us to essentially compute a linear combination of the other inputs and compare it to a threshold. And generally, if the inputs times the weights are larger than the threshold, then the perceptron unit fires, as in a human neuron. But usually we don't have this notion of firing. We just have essentially a function that's computing an output value, which is usually a continuous value. As I mentioned, each of the links from the input nodes to the next layer have weights on them. And so the next layer is typically called the hidden layer. And there actually may be multiple hidden layers in between the input layer and the output layer. Here we just have one. And as I mentioned, each of the nodes gets inputs from all of the nodes in the previous layer, and the outputs of those previous layer nodes are multiplied by weights, and then that linear combination of weights times the inputs is then passed into this hidden unit. Now the hidden unit then computes a function of the inputs to produce its output, and there are various choices for this activation function that sits inside these nodes. The default, at least for the scikit-learn and a popular choice in neural networks in general, is to use what's called a rectified linear unit. And here's a graph of what that activation function looks like, namely if the inputs the inputs times the weights sums to something less than 0, then the output is 0. But if it's something greater than 0, then the output is essentially linear in the inputs, or the same as the inputs. So the hidden layer is made up of these hidden units, these RELU units. And of course, the output of that is then passed on to the next layer. And again, there may be multiple hidden layers, so those are passed along layer to layer. But eventually we'll get to the output layer. And like all the other layers, the output units will take as input a linear combination of the outputs from the previous layer times the weights that are on these links. So here's the expression over here. And then of course the threshold unit always has an input of 1, and therefore the output is simply the weight times 1 going into the various output units. And then of course the output of the output nodes is this linear combination of weights times outputs from the previous layer. So the way that this network would make a prediction would be you would put the sensor data values at the inputs. Say we're just doing acceleration x and y. we let those values propagate through the network, until we get to the output layer, and of course the output layer would then produce the prediction. So that works by each of the output nodes corresponds to a particular activity, and whichever output node has the highest output, then the network would predict that activity for this particular setting of the input values. So for example, if we input the acceleration values and the work node may output a 0.8 and the play node may output a 0.2, then the prediction for the network would then be 0.8. So that's how the network is used, but of course we first have to train the network or fit it to the data, and the main way that's done is by modifying the weights that are on all of the links in the network. The math behind the weight updates is a little complicated, so I'm just going to explain it at a high level of what's going on. So again, back to our example, say we input an example which should be work, and the output of the work node is 0.8, the play node is 0.2, so that looks good, but ideally the output of the work node would have been 1 and the output of the play node would have been 0. So we have some error in the output. So again, for the work node, it should be about 0.2 higher. The play node, it should be about 0.2 lower. So the way we modify the weights is we basically will say, well, how can I modify the weights leading into this network in order to get rid of that error? And I can modify the weights accordingly. And then, of course, those weight modifications will cause a propagation back to the previous layer so that it modifies the weights to also get rid of the error. And so this is generally called error back propagation, which is how most neural networks modify the weights in order to improve their performance. Now, we don't want to make those weight changes all at once because the network will have difficulty converging if we make really large changes in the weights. So generally we just kind of nudge the network in the right direction by making small modifications to the weights in the hopes that over time the network will converge and produce a network and a set of weights that gets most of the training data right and hopefully other data as well. So that's how a neural network works in general. The neural network that's available in the scikit-learn package has a number of parameters, as do most neural networks. So I wanted to talk a little bit about some of the major parameters that you might want to change in the network. So the first set of parameters has to do with the topology of the network. Namely, you may want to modify the number of hidden layers in the network, and you may want to modify the number of hidden units in each of the layers. So in the scikit-learn neural network, there is a parameter called hidden layer sizes, which is essentially an array, and each element of the array represents a hidden layer. So in this case, which is the default value, there's just one hidden layer, and the number represents the number of units in that hidden layer. So we have one hidden layer that has 100 units. But I could add more values to this array, and as I add more values, I'm essentially adding more hidden layers, and the particular number I put in there will be the number of units in that hidden layer. And there's a lot of rules of thumb about the right number of layers, the right number of units per layer, but basically it's a parameter that needs to be tuned in order to get the best possible network. The next parameter that you may want to change is essentially the stopping condition for the training phase. So there's a parameter called tolerance, or TOL, and the way this works is that the network will continue modifying its weights until the performance of the network no longer increases by more than this tolerance. And when that increase in performance drops below the tolerance, then the network will stop and declare that it's converged. The tolerance here of 0.0001 is generally pretty good, so we're not going to modify that. but you may want to modify it if your network seems to be either converging too early or not converging at all. Another parameter that affects when the network stops training is just the maximum number of iterations. So each time it takes a pass through the data and modifies the weights and hopefully improves performance, that's an iteration. And by default, the network will do that 200 times. But in my experience, actually, that's fairly low. And to get good convergence, you generally want to go for many more iterations. So we're going to increase this quite a bit. But even if we increase it, in fact, we're going to increase it to 10,000, it may not necessarily use all 10,000 if the other convergence test is already passed. Lastly, I just want to point out that with a neural network, you typically want to randomly initialize the weights in the network in order to prevent it from getting stuck and not converge well. And what that means, though, is that every time you run the neural network and train it, you may actually get a different network out because it had a different random starting condition. And you might actually get different performance, and we'll actually see that when we run our code. So those are some of the parameters that you may want to modify in order to tune your network for best performance. All right, so let's take a look at the code. So again, this is the neural network.py file in the course materials. And as usual, we're importing our read data function. We're importing the neural network module from sklearn, and we're also importing the accuracy score metric from sklearn in order to compute the accuracy. Of those parameters that I mentioned, we're going to change two of them. First, we're going to add a second hidden layer. So we have two hidden layers, and both of them will have 100 units in them. And we're going to increase the maximum iterations up to 10,000. This last bit of code here we've seen before for reading in our sensor data. In this case, we're just going to read in the 3 acceleration values to be consistent with some of the other learners. But again, you can read in them all, and the network will adapt just fine. So here's the actual code where we train the network. So we're using the MLP classifier. This is the multi-layer perceptron, and we're passing in the 2 parameter modifications that we talked about earlier. So that creates our instance of the network. We then fit the network to our data. We then use that network to predict on the same data. We see how well that prediction Z here compares to the correct answers Y, and compute the accuracy, and then finally print that out. So let's try that out. So again, this terminal window is open to all of our code for the course, and we are interested in the neural network code. So let's run that. Okay, so we see that the output here, we have about an 89% accuracy. Well, let's run that a few more times and see if that changes. So I'll run it again. And sure enough, we get a different value for accuracy. And this is due to the fact that again, the network is initializing all the weights randomly. And so, some initializations work out to a better convergence than others. And I can keep running it. Again, getting different values. Looks like it's just oscillating between those 2 values. So generally, we're in the 89 to 91% range for accuracy for this particular network. Let me go back to the notes. So as I noted here, the accuracy can vary, but even so, the accuracy that the network is producing is quite a bit lower than what we saw for the decision tree in the last part. So, but again, there's a lot of tweaking we could do. We can add in the other sensor feature values and do a number of tweaks on the parameters for the network to try to improve its performance. So that's a very brief look at the neural network classification method. Now we've looked at a number of individual methods, but next we're going to look at the technique of actually combining multiple methods together in order to make a better prediction, and that's called ensemble methods.